Curve sketching example, we're looking at another rational function. We're looking at a special kind of rational function though, and I'll show you why in a minute. First off, anytime you have a rational, I would suggest first trying to factor both the top and the bottom and see what you get. In this case, we're going to have a difference of squares after I factor out that 2, which will give me a perfect difference of squares of x minus 1, x plus 1. To find the x-intercepts, I'm going to take this fraction now and set it equal to 0. When I do that, I should get just the top equals 0, so x plus 1 equals 0. That means x equals negative 1 would be the only x-intercept. Now, something you'd look at, though, however, is, well, look what happens here. We have a common factor on both the top and the bottom. That means that this guy right here actually ends up as a hole in the graph. We'll get to that in a second. So be careful, because if I have something that would have canceled out, that means it couldn't have been an intercept to begin with. So actually, this intercept is a bit of a lie to us. I'll talk more about that here in a moment. Okay, y-intercepts though, we're going to plug in 0. I should get 1 over negative 2. So that means my x-intercept happens at the point 0, negative 1/2. Okay, looking at asymptotes. Horizontal asymptote means I'm looking at the degrees. The degree of the bottom is bigger than the top. That means the bottom is growing more rapidly. So I'm dividing by a big, huge number. So my horizontal asymptote would be like 1 over infinity, which would be 0. Vertical asymptotes are when the bottom equals 0. So in our factored form, we should have x equals 1 and x equals negative 1. But again, this guy factored out. That means that this is not an asymptote. This is actually a hole in the graph instead. In our domain then, we just use our asymptotes, our domain errors, so negative infinity to negative 1, negative 1 to positive 1, positive 1 to positive infinity. All right, now we move on to the critical points, and we do that with a derivative. So I'm going to do my low d high, so x squared minus 2, 2x squared I should say minus 2 is low, derivative of the top is just 1, minus high d low. High is x plus 1, the bottom derivative would be 4x, all over low squared, so 2x squared minus 2, that whole quantity squared. Okay, I'm going to simplify the top. I'm going to get, I should get 2x squared minus 2, and then minus a 4x squared minus 1, all over still the same bottom, 2x squared minus 2, the quantity squared. And up top, it means I'm going to get a negative 2x squared, and I should get a, it should have been here a minus 4x. So it should be negative 2x squared minus 4x minus 2 over, this will be 2x squared minus 2 quantity squared still. So let's keep trying to simplify this. Up top, I can factor out a negative 2. I'm going to factor out a negative 2 because I don't want a negative x squared. So it will be x squared plus 2x plus 1. And on the bottom, still keep it the same right now, 2x squared minus 2 quantity squared. What I'm going to do from here, I'm going to factor the top. This will be x plus 1 times x plus 1. On the bottom, well, what I should notice, this whole guy squared, well, we already simplified it to be this thing, and then we're squaring it. So each one of these values can be squared to simplify that. So 2 squared is 4. This will be x minus 1 quantity squared. This will be x plus 1 quantity squared. Now I can simplify and see, well, 2 divided by 4 will be a negative 1 over 2. My x plus 1 squared here on the bottom cancels out with both x plus 1 terms up top. So that means all I'm left with is an x minus 1 quantity squared on the bottom. And that is my first derivative after all that work. So now, after all that work, to find the critical points, I set that guy equal to 0. That means that I set the top equal to 0. Well, when does negative 1 ever equal 0? It never does. So I cannot have a critical point. That means I can't have a relative min, I can't have a relative max, either way. I can, however, still have increasing and decreasing intervals. Because remember, on my number line, not only do I plug the critical numbers, well, there are none, I also plug in any domain issues, any asymptotes. So at x equals 1 is the only thing I'm going to plug in. So no matter what happens here, though, take a look. I'm plugging in a number and squaring it. That makes it positive. Multiply by a positive number, so it's still positive, and then dividing it by a negative number. So I'm going to, no matter what, get a negative value around that asymptote. So that means I'm never increasing, I'm always going to be decreasing. So negative infinity to 1 and 1 to infinity are your intervals. Points of inflection now deals with the second derivative. And because we did all this simplifying earlier, makes my second derivative a lot easier to compute. I'm still going to do a quotient rule. So first I'm going to do low d high. So here's the low times d high. Well, derivative of a number is just 0. So that whole thing's going to go away. Minus high d low. Derivative of the bottom. Chain rule. Bring the 2 out in front. 2 times 2 is 4. Times x minus 1 in the first power, keeping the inside the same, times derivative of the inside, which is 1. All over low squared. So 2 squared becomes 4, and then x minus 1 to the 4th power. Again, this whole guy is multiplied by 0, so it's going away. What I'm going to have here as well is the, I have an x minus 1 in both the top and the bottom. So they should cancel out. And what I should be left with now is whatever's up top. So negative 1 times 4 times 1 is negative 4, but it's minus negative 4. So it should be a positive 4 over 4 times x minus 1 to the 3rd power, which I can simplify even more to be 1 over x minus 1, the quantity cubed. So that means to find the points of inflection, again, I just set it equal to 0. If a fraction equals 0, that means the top equals 0. That can never happen yet again. So that means I have no points of inflection. But again, when I draw my number line, I need to include any asymptotes that I have. So to draw on that asymptote again, if I plug in something that's negative here, I'm going to have a negative number cubed, which would be negative. If I plug in something like 2, I'll have a positive number cubed, which will be positive. So that means that it is concave up when it's positive, from 1 to infinity, concave down when it's negative, negative infinity to positive 1. So now it's time to graph this sucker. And what we're going to do is graph all the asymptotes first. So there's a horizontal asymptote at y equals 0. Graph that guy first. Now we'll graph intercepts. There were no x-intercepts, which there shouldn't be because it was an asymptote. Y-intercepts happen at the point 0, negative 1/2, so that's where that point's going to be. What else do I know? I know that there's no points of inflection, anything like that. I do have a vertical asymptote, though, at x equals positive 1. And now I should try to draw this graph, okay? So what's going to happen here? There's not much to go by, but what I can find out, though, is that I'm always decreasing, and I have to go through this point. So the only way I can follow the asymptotes and go through that point is something like that, okay? And also something you remember, we had a hole at negative 1, so I should be drawing an open circle at that point. And I probably should even use the eraser here and erase that part on the inside to make it look like a legitimate hole. So there's your hole value going there. Now, the only thing we have to figure out from there, though, is whether this second part is going to be up here like this to follow the asymptotes, or down here to follow the asymptote that way. Well, something we should look at, it's always decreasing and it's always concave up. The only way that can happen is if it's on the top part of the asymptote instead of the bottom part. So I'm going to look just at the top part as it is written right there. Another way you could check that for sure, if you plugged in, for example, positive 2, you would get a number like 3 up top and, what would you get on the bottom, 6, so like 1/2, but it would be a positive number, so you know it has to be somewhere up top. And that's the best way that you can try to sketch it and make sure you're on the right side of those vertical and horizontal asymptotes. And there you have it. That's your basic sketch for a graph with a hole. Again, make sure we pay attention to, it was an intercept, but it ended up being a hole, so it couldn't be an intercept, and also because it was your asymptote anyway.